Some Academy, and today's topic is part of chemical energetic. Today's topic is part of the chemical energetic, and we take a look at 3.1.2, which is calorimeter. We briefly look at calorimeter, and then we can go to the next one, the energy calculation, in chemical reaction. So calorimeter is just a technique that is used to measure changes in enthalpy of chemical reaction. Okay, in a technique that we normally use to measure the changes in the enthalpy, in the energy change in any chemical reaction. And there are two major types of experiment that we normally do with this calorimeter, which are called the calorimetric experiment. One of it is called the enthalpy changes of reaction in solution, and then the second one is called the enthalpy changes of combustion. Now let's take a look at the first one, which is the enthalpy changes of reaction in solution. Okay, so reactions in solution. First and foremost, when we're looking at the reaction in solution, the first thing we look at is the principles of this calorimetric experiment, the principle with which we use in carrying out the calorimetric experiment. And these principles of this experiment is to carry out the reaction with an excess of one reagent and measure the temperature change over the course of few minutes or few time lag. Okay, so we just take a look at for example, we take into cognizance one of the reagents, and then we measure the other. Usually we measure the temperature change over time. Okay, then this technique is we say is well suitable and is suited for reactions such as things that are dissolving, like you dissolve salt in water, you dissolve sugar in water, anything that dissolves, this type of, because that forms a solution, this type of reaction is very suitable for it. Not only dissolving, things that do dissolve, we also look at things that undergo displacement and neutralization. Things that neutralizes completely in a solution, two aqueous that can neutralize themselves to form to form other compounds or other substances. So those type of reaction form solutions. Those type of reactions, they form solution. Things that completely get displaced when the reaction takes place, they also fall into this type of solution case. Now, the technique is suitable for reactions such as dissolving, displacement, and neutralization. For the purpose of calculation, some assumptions are made about the experiment whenever we're doing this experiment. One of such assumptions that you've learned in physics is the specific heat capacity of the solution. So one of the assumptions we do make when we are carrying out this experiment is the specific heat capacity of the solution. Okay, we assume it to be the same as that of water. Approximately we call it 4,200 joule per kilogram per Kelvin. Okay, joule per kilogram per degree Celsius or whatever. Okay, but more specifically is 4,180 joule per kilogram per Kelvin. But if you are using gram, if you are not using kilogram, you can just say 4.18 joule per kilogram, joule per gram per Kelvin. If you are using gram, you just say 4.18. If you're using kilogram, this will be 4,180. Is that okay? Please take note of this. So this is one of the assumptions we made. Because the solution, we don't know the specific capacity of the solution. We just assume it to be same as the specific capacity of water. We assume it to be same as the specific capacity of water. Another assumption we quickly make in carrying out this experiment is the density of the solution, which we also don't know. We also don't know the exact density of the solution. So we assume it to be the same as the density of water. We quickly assume the density of the solution to be same as the density of pure water. And that is 1 gram per centimeter cube. 1 gram per centimeter cube. Or more specifically, you can say 1,000 kilogram per meter cube. 1,000 kilogram. Okay? So remember, when we're using kilogram, we multiply with 1,000. When we're using kilogram, when we're talking in terms of kilogram, not gram, we multiply these values with 1,000. So for this one, it's 1,000 kilogram per meter cube, or if you say gram per centimeter cube, you just say 1 gram per centimeter cube. Okay, this is another assumption we make because we don't know the density of the solution. We don't know the density of the solution. Okay, but we can just make a quick assumption to be same as the density of pure water. We make it a quick assumption. It's just an assumption, scientific assumption, to be same as the density of water. Then another assumption that is very important is the specific capacity of the container. This one we can ignore. Okay, we can ignore the specific capacity of the container. Okay, then the reaction is complete. Then there are negligible heat losses. Obviously, when an experiment is carried out, there are negligible, small, tiny heat losses here and there. Okay, due to conduction or other reasons. We can accommodate, but two basic assumptions we make in this experiment is specific capacity of the solution, and remember we are talking about reactions in solution. We make quick assumption of the specific capacity of the solution. We assume it to be same as the specific capacity of water, which is 4,180 joule per kilogram. Okay, when you say 4,180, or more specifically, approximately 4,200 joule per kilogram per degree Celsius. So if you are using gram and Kelvin, it will be 4.18. Is that okay? Then another assumption I say we make here is the density of the solution. We assume it to be density of same as the density of pure water. So which is 1,000 kilogram per meter cube, or 1 gram per centimeter cube. So having said this, then we look at how we carry out the experiment. Okay, here we have the thermometer to measure the temperature. We have the thermometer to read the temperature. At the moment, it's reading a temperature of 0.2 degrees Celsius, right? Then we have a plastic lid here to prevent heat loss. A plastic lid to act as insulator. To prevent the heat from being lost. Then we also have a plastic, what you call a polystyrene cup to also prevent heat loss. These are all insulating materials, okay? Because plastic is an insulator, it's not a conductor. So the essence of using this polystyrene material is to prevent heat loss, okay? It's to prevent heat loss in the process. Then we have the reaction mixture, the solution itself. The reaction mixture is brought in here. So we say this is a polystyrene cup, and this polystyrene cup can act as a calorimeter to find enthalpy changes in the chemical reaction. It can help us to find the enthalpy changes in the chemical reaction. Okay? So we say a fixed volume of one reagent is added to the calorimeter, and the initial temperature is taken with the thermometer. So we take the initial temperature with a thermometer. The moment we add any one specific reagent, any specific reagent that we are using that form the solution. So we say a fixed volume of one reagent is added to the calorimeter, meaning you have to measure that volume, maybe 100 centimeter cube, or 50 centimeter cube, or 25 centimeter cube, or 20 centimeter cube, based on your presumption for the experiments. Okay. And then once you do that, then you take the initial temperature, okay? You take a specific volume of the reagent that you're using, and then you take the initial temperature. Then we go to, when the experiment takes place, we go to take out that temperature and see what will be the final temperature. Now, an excess amount of second reagent, you add again. It depends on what your reagents are the things that are forming your solution. The 2 things or 3 things that you're adding together to form your solution. Okay, so an excess amount of the second reagent is added and the solution is stirred continuously. This is what you do, okay? First, you add your first reagent. You take the initial temperature. Then you add the second reagent. You take your second reagent. You add it to it, okay? And then you stir it gently and see what you have, okay? Then after you've done that, the next thing is that we look at the maximum temperature is recorded and the temperature rise is calculated. So now, after you stirred it so warmly, then you will see after reaction has taken place, the maximum temperature will be recorded quickly, and then you can calculate the temperature rise by saying the the final temperature minus initial temperature. Then we'll be able to get the temperature rise. So this is how we can measure temperature of reactions in solution. Temperature of reactions in solution. Now let's take a look at the enthalpy of combustion experiment. In the case of enthalpy of combustion, you remember we say for calorimeter measurement, we have two: enthalpy of solution and enthalpy of combustion. Enthalpy of solution and enthalpy of combustion. Now let's take a look at the second one. Enthalpy is just like you're measuring the heat energy. That's it. It's just like you're measuring the heat energy, the thermal energy. Just the measurement of the heat energy when reaction takes place. The first one is for solution. So whenever you have a solution, how do you measure the heat energy? Amount of heat that generated when the reaction takes place. That's what we mean by the first one. Now this second one, enthalpy of combustion, is what happens when a combustion reaction happens. Okay, the heat energy that is given off when a combustion reaction happens. You know, combustion is when a fuel or anything that can act as fuel react with oxygen, right? And then to produce water, produce carbon dioxide, and so on and so forth, and heat energy. So, in saying so, for this experiment, the principle here is use the heat released by the combustion reaction to increase the heat content of water. We use the heat released by the combustion reaction. The heat released by the combustion reaction. Combustion is burning, simply burning. So the heat released by the combustion reaction, we use it to increase the heat of the content of the water. And there we measure the temperature. We measure the temperature. Is that okay? So here, a typical simple calorimeter is used to measure the temperature changes to the water. Temperature changes to the water. Here you can see we have an insulating lid so that the heat will not evaporate away. The heat will not get lost, will not evaporate. We have a thermometer to measure the temperature changes. We have a drought shield to ensure that there are no moist or other things coming into this experiment. We have a spirit burner to provide the heat. We have a copper can, a copper can so that the heat can go in. This is a metal to supply the heat. You know, metal is a good conductor of heat. So the copper can act as a conductor to enable the heat to get to the water, just like your cookie pot. Okay? You put the food in your cookie pot, you heat the cookie pot, the heat gets to the food. Similarly, this copper can get heated through this triple stand, and then the water gets the heat from this combustion reaction. Remember, combustion is simply burning. So we can now measure the temperature. So we measure first the initial temperature, and then we measure the final temperature after you supply the heat from this spirit burner. Is that okay? And here is your water that you heat here, and you're finding the temperature changes. Okay, so a typical one is the one we've just seen when you use the water. Now, a fixed volume of water must be measured and poured here. You must know the volume of water that you're adding here. Okay, it's very important. It's very necessary. Okay, so you must measure a specific volume of water and you pour it in the copper can. Then the spirit burner containing, for example, an alcohol is weighed on a 2 dp balance. You weigh this one, and then we use it to supply the heat that is needed to get the experiment going. Then the initial temperature of the water is measured and recorded. First you measure the initial temperature of the water, and then you record it. Then the alcohol is ignited and the water is stirred continuously. So before you ignite this one, you first measure the initial temperature of the water. Before you ignite this alcohol substance, the spirit burner, you know it contains alcohol. Before you ignite it and start burning, okay, the spirit burner that contains alcohol, you know it's a fuel. So you burn it. Before you burn it, you first of all take the temperature of the water. We call it the initial temperature of the water. And then when you start burning, you stir the water. After a while, a given period of time, you measure the final temperature of the water. And then you find the temperature rise by saying the final temperature minus the initial temperature. That gives you how much heat came in, how much heat. That gives you an estimate of how much heat energy came into this reaction. Okay, now we say that when the temperature has risen by about 20 degrees, the flame is extinguished and the spirit burner is reweighed. You reweigh this one, okay, you put the fire off, the flame off, and then you also take your temperature. the final temperature. Okay, you measure the final temperature of the water when this has happened. Okay, now in your experiment, what are the sources of error? In paper 6 chemistry, they always talk about the sources of error. They always talk about sources of error. In every experiment, there are unique sources of error, but there are some sources of error that you can use in every experiment. Okay. One of the sources of error is that not all the heat produced by the combustion reaction is transferred to the water. Yes, not all the heat go here. Some will come out from here, right? You know, right? Some of the heat energy can come out from this place. So that's one of the source of error. Not all the heat. So you may not be able to measure the exact, because the whole experiment is to measure the amount of heat energy that is transferred here. Amount of heat energy. That's what we call the enthalpy of combustion. The enthalpy is the energy, heat energy, like I said before, the heat energy. So the whole essence of the experiment is to measure the heat energy that was supplied to this water. So, but one of the errors that may occur in your experiment is that not all the heat energy that the spirit burner produced, all of them heated the water, not all of them. So some of them escape from these corners and through the down part of the triple stand and escape out of this place. That's one source of error. Okay, we say some heat is lost to the surrounding. You lost some heat to the surrounding, and some heat is absorbed by the calorimeter itself. Some heat is absorbed by the calorimeter. This conductor, this thing itself, this can itself. Some is absorbed. Not all went into the water. Not all of the heat went into the water. So some are lost to the surrounding, and some are being absorbed by the calorimeter itself. There. How do you now minimize these errors so that you can get great experimental result? How do we minimize the error in order to get a great experimental result? One, in order to minimize the error, we have to you have to find a way to minimize the heat loss. Okay, the copper calorimeter should not be placed too far above the flame. Should not be too far above the flame, and a lead placed over the calorimeter so that it will help the energy to be retained, the heat energy to be retained. So we should not take this the copper can too far away from the heat flame. It should be close, should be super close, so that we can maximize the energy that is being supplied. We can maximize it. Okay. Another thing is that shielding can also be used to reduce drought. We shield this environment in order to reduce drought. Okay. So another thing is that in this experiment, the main source of error are heat losses. We already itemized that. The heat losses are one of the biggest source of error. The heat could be lost from this bottom, this part, so to the surrounding, to every one of them. Then incomplete combustion, meaning no enough oxygen for a complete combustion of the fuel. No, whenever the oxygen is not in the excess supply, there will be an incomplete combustion. Once the oxygen is not in excess supply, there will be complete combustion. Let's have a dilly-dally about that. Let's have a look at that. Okay. Let's quickly have a look at that. Okay. So we say like a fuel is like fuel plus oxygen. You know, if you take fuel, you say plus oxygen for combustion reaction, plus oxygen, then we will get what? We will get complete. If the oxygen is in excess, we get a complete combustion. If the oxygen is not in excess, we'll get an incomplete combustion. Okay. When this happens, we get carbon dioxide and water and so on and so forth. So I can use since it's a spirit, we can use as an alcohol. We can use this CH. We can use CH. C2H5OH. We can use this as our fuel. We're going to do organic chemistry soonest, okay? In fact, I think when we finish this big chapter, we can go to organic chemistry straight away. Then when it bonds with oxygen, then we can have what we call CO2, carbon dioxide. If there's a complete combustion, it will produce CO2. If there's incomplete combustion, it will produce carbon monoxide, which is super dangerous. Okay, so if there's complete combustion, there will be this produced water, okay, and also plus energy. This energy is heat energy, of course. This energy is what? Heat energy. Okay, plus energy. So this is excess. We always make sure there's excess oxygen. Once the oxygen is in excess, once the oxygen is in excess, then there will be a complete combustion. There will be a complete combustion. Okay? Okay, so this is what happened. When the spirit burner, we can assume is alcohol. Okay, it burns in the presence of oxygen and it produces carbon dioxide, water, and energy. Is that okay? Now let's quickly go back to what we have. So sources of error in your experiment is the heat loss and incomplete combustion. Is that okay? Okay, now let's go to some energetic calculation. Okay, these calculations are in physics. If you've done this in physics, this is a specific capacity calculation. Okay, these are in physics. So we take a question, we solve it on the board. But before we do that, let's quickly explain this part. We say this one is calculate the heat energy change. How to calculate the heat energy change. So in order to calculate the heat energy change, in order to calculate the heat energy changes, you need to know the mass of the substance. We need to know what? The mass. One is the mass. So let's say heat energy. Heat energy change. So if you want to do that, we need to know the mass of the substance, we need to know the specific heat capacity, and we need to know the change in temperature. That's the difference between the initial temperature and the final temperature. Okay, once you know this, then you'll be able to calculate the heat energy change, or what we call the heat energy change. You'll be able to calculate that. So the first thing we need to know is the mass, right? So we need to know the mass of the substance. We need to know the mass of the substance. We need to know the specific heat capacity. We need to know the specific heat capacity of the substance. We need to know the specific heat capacity. What is this specific heat capacity? We just measure a term. This is in physics. What is specific heat capacity? Specific heat capacity is the energy required, the energy needed to raise a unit mass of a substance, a unit mass of 1 kg of a substance through 1 degree Celsius. Okay, the energy you need to raise a unit mass of a substance through 1 degree Celsius. So let's say I have 1 kg of an ice, 1 kilogram of an ice. The energy I need to raise, let's say if the temperature of this 1 kg of ice was 0 degree, let's say the temperature was 0 degree, the amount of energy I need to raise this temperature to raise this temperature to 1 degree. The amount of heat energy I need to raise this temperature to 1 degree Celsius is called the specific heat capacity. Okay? There must be mass. Please pay attention. What is specific heat capacity of a substance? The specific heat capacity of a substance is the energy that we need to raise 1 kg of a substance, 1 kilogram of a substance, meaning there is mass. The energy we need to raise 1 kilogram of a substance through 1 degree Celsius. The amount of energy that we need to raise 1 kilogram of a substance through 1 degree Celsius. So I say, for example, if you have 1 kg of ice, 1 kilogram of ice, 1 kg, okay, of ice. let's say you weigh it, you know that this is 1 kg of ice. The amount of energy that you need to raise the temperature from 0 degree to 1 degree, that heat energy that can raise it through 1 degree Celsius from 0 to 1, that or from whatever temperature from 2 to 3, but there must be through 1 degree Celsius. If it was already in 4 degree, it will raise it to 5 degree. That heat energy that can do that for you is called specific heat capacity. It's called the specific heat capacity. And you also need the temperature change or change in temperature. We need the temperature change. The final minus initial temperature is called temperature change. So when we say temperature change or change in temperature, we are saying the final temperature minus the initial temperature. Okay? We are saying the final minus initial temperature. The final temperature minus the initial temperature. So, which we write like this, delta T, change in temperature, okay? This is what we need for our calculation. Is equal to, if you know it here now, you also learned it in physics. Is equal to, I think we did it last time in physics also, I remember. So, this change in temperature is equal to T2 minus T1. That means the final temperature minus the initial temperature. Assuming T1 is initial temperature and the T2 is final temperature. Okay, now let's put this specific capacity. I love to put C small s here. Okay, so most of the textbook they don't put this s. I just love to put it. Okay, and then the mass you already know is m. Okay, so the energy, to calculate the energy now, to get the energy, because this is about calculating energy for reaction, for the heat energy that occur during chemical reaction. How do we calculate the energy? So this energy, we've done this in physics before, so we can compare it as fast as we can. So this energy, we can say delta E. Okay, this delta means a change in energy, means change. Okay, this change in energy is equal to the mass of the substance, multiplied by the specific heat capacity of the substance, multiplied by the specific capacity of the substance, multiplied by the change in temperature, multiplied by the change in temperature. So I can call this equation 1, right? We can call this equation 1. And then if we want to find the specific capacity from an experiment, we make it the subject of formula. So this Cx will be the energy divided by change in energy divided by the mass times change in temperature. So this one divided by mass and temperature. Mass times change in temperature. So this will be our second equation for this heat energy calculation in chemistry. Is that okay? So let's quickly take a look at what we're talking about. So once we've done that, we say we've already stated what is specific capacity. We say it's the energy that is required to raise 1 kg of a substance through 1 degree Celsius. The amount of energy. So sometimes they can use gram instead of kilogram. Okay, they can use gram. If you are using gram, you have to be consistent throughout. So if you are using gram, you use centimeter, you use Kelvin. But if you are using kilogram, you use meters. Meter for volume, you use meter cube. You use degree Celsius. Okay, so you have to be consistent. But it doesn't matter. We can easily convert units from one form to another. Now the specific capacity of water is for kilogram. You know it's a fixed value. But most especially for IGCSE, I think we just take an approximation. Cx, specific capacity of water. So if I put W here, specific capacity of water, it's approximately 4,200 for convenience. 4,200 for convenience. 4,200 joule. If you're using kilogram, it becomes joule per kilogram per degree Celsius. Okay, but if you are using gram, this value is still same as, you can say 4.2, just 4.2 joule per gram per Kelvin. Okay, per gram per Kelvin. Okay, you know they can write per gram like this. Joule per gram can be written like this. Okay, you can write joule per kilogram like this, right? Like joule over kilogram. You can also write like this, joule, then you write kilogram raised to power minus 1. So don't see this and be It's just showing that we are good with mathematics, with indices. Okay, you can write like this, because joule, this one means joule over kilogram, for example. This one, joule per kilogram is joule over kilogram. So if joule per kilogram is joule over kilogram, in indices, joule is in the numerator, so it's like you say J times 1 all over kilogram. It's like you say J times 1 all over kilogram in indices. Okay, 1 all over NET is 30 raised to power minus 1, you know, right? 1 all over NET is 30 raised to power minus 1. So that's why it's also mathematically correct to write like this, joule kilogram raised to power minus 1. Okay, that's why it's mathematically correct to write like this. Is that okay? Now let's quickly move on. So the specific capacity of water is 4,000 for convenience for IGCSE. It's same as 4,180. Okay, this is more specific value. This is the more specific value. 480 joule per kilogram. Okay, if you are using gram, this joule per kilogram per degree Celsius. If you are using gram, this will be 4.18 only. 4.18 joule per gram. Joule per gram per Kelvin. This time not degree Celsius, per Kelvin. If you are using gram, okay. So don't be confused when you see these values. Okay. Now let's and then you think we are not consistent. We are. The energy transfer as heat can be calculated as what? Like this. Okay. This is the mass. This Q is the one we use E for. Okay. Some textbook they use Q here. You can use Q, delta Q. Okay. You can use delta Q as your energy. It's also a symbol. The mass, okay, this is equals to the energy equal to the mass times specific capacity. You know, I told you some text they don't put small s here. I used to put to show that it's specific heat capacity. Okay, so mass times the specific capacity times change in temperature. All of these parameters have been defined here. Now let's take a look at a problem and let's solve the problem, right? Let's take a look at the problem and see how we can solve the problem. Now we say excess iron powder was added to 100 centimeter cube of 0.2 mole per dm cube copper 2 sulfate solution in a calorimeter. Okay, so we know the volume. We can write out the volume. You know, we can convert this volume to decimeter cube by dividing with 1000. If you want to change this volume centimeter cube to decimeter cube, you just divide with 1000. Okay, it's not a big deal because this is in mole per decimeter cube. Okay, the mole is in decimeter cube. So if we are doing any molar calculation, we have to change this one to decimeter. But I think for this question we don't need volume, so we don't have to bother ourselves. Excess iron powder was added to 100 centimeter cube of 0.200 mole per decimeter cube copper 2 sulfate solution in a calorimeter. The reaction equation was as follows. Look at the reaction. Iron plus copper 2 sulfate producing iron sulfate plus copper. So we write the equation, and the maximum temperature rise was, you know, this is temperature rise. That means this is already the change in temperature. But once they say temperature rise, they are already talking about the change in temperature. Now determine the heat energy change of the reaction in kilojoule. Determine the heat energy changes in the reaction. So we're going to find mass. There are one or two things that we're going to do. We're going to calculate the mass. If you don't find the mass, okay, we will not be able to solve this equation. So we say the solution is assumed to have the same density as water. Okay, the density is same as that of water, and the mass of 100 grams. So they assume this mass, okay, to be 100. They assume the mass to be 100 because they assume the density to be same as that of the density of water. So if you use that and this volume, you will get this mass. If the density is same as that of the density of water, which is 1 gram per centimeter cube, okay, if the density is 1 gram per centimeter cube and the volume is 100 centimeter cube, now we can get the mass in gram. So if you come here, this is one absorption they made for this calculation, that the density of this solution is same as that of pure water. You know, I told you we can make such assumption. Okay, so since we know that density is equal to mass over volume, You know, in the question, in the problem, they gave us the volume. They said V was 100 centimeter cube. They said V was 100 centimeter cube. Okay, since V volume is given to us, and the density of water is 1 gram. If you are using gram, the density will be 1. The density of water is 1 gram per centimeter cube. 1 gram per centimeter cube. This is the density if you are using gram. But if we are using kilogram, this will be 1,000. Okay, this concept we already talked about them. So if you bring the density, substitute to this equation, we can calculate the mass. So the density is 1, so we put 1 here, is equal to, what's the mass? We don't know. That's what we're looking for, over the volume. Volume is 100. So here, all we need to do is to cross multiply, right? All we need to do is to cross multiply. So if we cross multiply, we have the mass to be equal to, 100 gram. We have the mass to be equal to 100 gram. Okay, now that we have the mass to be equal to 100 gram, remember what the question wants us to find. The question wants us to determine the heat energy change of the reaction. The heat energy change of the reaction. Okay, let's write the equation. Iron plus copper sulfate form iron. Okay, let's write the equation. Iron plus copper sulfate. Iron is a solid. Okay, iron this is the state symbol. We're saying that it's a solid. Plus copper sulfate. Copper sulfate is aqueous, right? Plus copper sulfate, CuSO4, copper 2 sulfate. The state symbol is aqueous, right? This will produce iron sulfate. This will give us iron sulfate. Iron sulfate. This will give us iron sulfate plus copper, because this copper will be displayed. Iron is higher than in reactivity series than copper, so it will display copper. It will become iron sulfate and then plus copper as a solid. Copper as a solid. Okay, so this is what we have. This is the equation of the reaction, right? This is the equation of the reaction. And then temperature rise is at 7.5. So our temperature, change in temperature, we know the mass, change in temperature is 7.5, right? 7.5 Kelvin. Change in temperature is 7.5 Kelvin. And our mass is 100 gram. Our mass is equal to 100 gram. So we can calculate the heat energy, 100 gram. Specific capacity, for this case, we assume to be same as that of water. Specific capacity, we assume to be same as that of water, which is 4.18, 4.18, 4.18, 4.18 gram 4.1 joule per gram per Kelvin. So this is what we're going to use. So our energy will be what? So the energy, you can use delta Q or use delta E. It's up to you. For this case, I think we are using E for us. So this will be MC small x subscript at delta T. This is the temperature rise. Delta T is temperature rise. So the mass is 100. We say 100 multiplied by 4.18 or 4.2. You can say 4.18 or 4.2 times 7.5. So when you do this, what do you get? Okay, can you press this quickly? What do you get? When you do this, you will get what do you get? You get 3,135, right? 3,135. We put negative because it's an exothermic reaction. we get 3,135 joule per kilogram per gram, joule per gram per Kelvin. Joule per gram per Kelvin, which, remember, they say we should leave our answer in kilojoules. So you divide by 1000, become 3.135. You want to leave your answer in kilojoule. So you get this one, kilojoule per gram per Kelvin. So this will be your answer, okay? So this is how we start solving questions. This is way related to physics, so this is not an issue, okay? Now let's see if there's any other example that we need to look at. But let's take a look at this second example, okay? We say they've given us the mass for this one, a 1.023 of propan 1-ol, okay? This is an alcohol family. A 1.023 propan 1-ol, M equal to 60.11 gram per mole. Okay, this is the concentration, okay, per mole. Then was born in a spirit burner and used to heat 200 gram of water in a copper calorimeter. It was used to heat 200 gram of water in a copper calorimeter. Now the temperature of the water rose by 30 degrees Celsius. The rise is the change in temperature. Now calculate the heat energy change of the combustion of propan 1 using this data. Okay, so first of all, we're going to look at the data that we have that will enable us to calculate the heat energy. The heat energy formula we already know, where is MC delta T, right? We already know. So the mass of the substance of the water is 200 gram. Okay, the mass of the water in the calorimeter was 200 gram, right? So that will be our mass. Then we know the specific capacity of water, 4.18. Then the temperature change is 30. So in this case, we are using 30 Kelvin, not degrees Celsius. Okay, so since everything, so when we do this, we will get our energy. We get our energy when you multiply all of this one out. You multiply 200 times 4.18 times 30, you get 25,080. So joules, kilojoules. Is that okay? Okay, sorry, the one we calculated, the unit was, this unit is just joules, not per degree. This one is for specific capacity. This unit is for, so this is just joule, unit of energy. Okay, it's just joule. This one is cancelled, okay, please. This is cancelled. This is the unit of this one is now kilojoule. Just kilojoule, okay? Just kilojoule. Because you are calculating for energy. Once you are looking for energy, the unit is joule or kilojoule. This unit we wrote before was for the specific capacity, this one. It is the specific capacity that has joule per gram per Kelvin or joule per kilogram per degree Celsius. Okay? So let me quickly correct that. Now let's move on quickly. Now calculate molar enthalpy change. How to calculate the molar enthalpy change? Molar enthalpy change is the heat energy change per mole of a substance. The heat energy that changes per mole for every 1 mole. The heat energy change for every single mole of a substance. Now the symbol is delta H. The symbol for molar enthalpy change is delta H. For molar, we say molar enthalpy change. Enthalpy, molar enthalpy change. The symbol is delta H. Okay? So we said the symbol for molar enthalpy change is delta H. And now we're going to find the heat energy per mole that takes place for every unit of mole in a reaction. Now the symbol we already say, so we can have we can calculate this one in the unit of kilojoule per mole. Now, if found by first determining the heat energy change of a reaction, so in order to do this, you have to find the heat energy change that we just talked about. You have to calculate it first before you can calculate the molar enthalpy change. So you calculate that, you divide by number of moles. So what you did just now, you just do it, you divide by the number of moles. You do the same calculation of heat energy change. When you finish the calculation, you divide by the number of moles, then you get the molar enthalpy change. Now here is a question which we're going to evaluate. So first of all, it says the energy of 0.01 mole of propan ore was used to heat up 250 grams of water. Now the temperature of the water rose to 298 Kelvin. Rose from 298 Kelvin to 310 Kelvin. So we're going to find the energy change by saying 310, temperature change by saying 310 minus 298. So you're going to find the temperature change by saying 310 minus 298. Now the specific capacity of water is given to be 4.18 joule per gram per Kelvin. Calculate the molar enthalpy of combustion. So the molar enthalpy of combustion, first of all, you bring everything out. You bring the mass of water, we bring it out. We write the mass of water, the specific capacity, and the change in temperature, we bring it out. So before we calculate this molar enthalpy is delta H, we have to bring our mass. Our mass was what? What was the value of the mass? Is it 250? Mass was 250 gram. The specific capacity was 4.18 joule per gram. So I do per gram raised to power minus 1 like this, the Kelvin. Okay, then the change in temperature, delta T, okay, change in temperature, delta T is T2 minus T1, T2 minus T1, okay, which is equal to 310 minus 298. So this will be equal to 12. This will be equal to 12 Kelvin. This will be equal to 12 Kelvin. So the energy, to calculate the energy now, so we calculate this energy by doing this. We say delta E or Q. You know, I said you can call it delta Q, right? So delta Q or delta E is equal to mCx delta T, right? So we do this first. So you put the mass 250, if we're not mistaken, 250 gram multiplied by this value of the specific capacity, which is 4.18 joule per gram per Kelvin, there times the change in temperature, which is 12 Kelvin. So when you multiply all this out, what do you get? What do you get? When you multiply all this one out, what do we get? We get 12,540, right? We get 12,540. Okay, so we come here, we say 12,000. We get 12,540. Joules. Remember, this is the energy, joules. Okay, so now we get the heat energy changing. We get the heat energy changes. Now we get the heat energy changes. So after the heat energy changes, now we calculate the molar enthalpy change. The molar enthalpy change is delta H. Like we said, molar enthalpy change is delta H, which is your delta E or delta Q. This is your delta E or delta Q. You know, we can use any of them. okay, which is your heat energy changes. This is called delta Q is heat energy changes. Divide by number of moles. N, we use small letter n for number of moles. We use small letter n for number of moles. So remember in the question, we say we've already calculated this heat energy changes. We already calculated what? We already calculated this heat energy changes, which is 12,540. 12,540. 12,540 divided by number of moles. Remember the number of mole in the reaction 0. What? 0.01. Okay, this is the number of moles, 0.01 mole. So we divide by 0.01 mole. We divide this by 0.01 mole. This is joule. So can we divide quickly? Can we divide quickly? What do you get? When you divide, what do you get? What do you get? What do you get? 12,540. 12,540 divided by 0.01. 01. What do you get? Okay, you get 1.1254 thousand. Okay, 1,254,000. So we get 1,254,000. We get 1,254,000. 1,254,000 joule per mole. Joule per mole. Okay, this is molar energy change. Okay, molar enthalpy change. So, but this one is we can reduce to kilojoule because it's so big. We can even reduce to megajoule by dividing by 1 million. Okay, if you divide by 1 million, you will get 1.254 megajoule. Okay, megajoule. So, but we can just put in kilojoule by dividing by 1,000. If you divide by 1,000, you get 1254. You get 1254 kilojoule per mole. This is the amount of the enthalpy change, molar enthalpy change. This is the amount of the molar enthalpy change that has occurred in this calculation. Is that okay? Okay, so this is what they have done. This is the negative is showing that is an exothermic reaction. So I think for today we stop here. We stop here for today. Next class we've taken calorimeter energy calculation. Next one I think we're going to what we call the energy level diagram. Okay, we're going to the energy level diagram. So we stop here for this class. Thank you very much. Thank you.